The force of gravity. So far, we have learned a little bit about the acceleration caused by gravity, but now we're going to see the bigger picture of what the force of gravity is all about. So, the person responsible for much of what we know about how gravity works in the mathematical models of gravity is Isaac Newton. He basically explained a lot about gravity. And then, of course, Albert Einstein came along later and filled in the holes. Albert Einstein actually gave us a whole different picture that, is probably an improvement on what Newton thought. But Isaac Newton's stuff isn't old and useless. Still works perfectly well under many situations. So we still use it all the time. Isaac Newton's gravity is what we use to put men on the moon. So we didn't need Einstein's help to do that. So these things that we're about to learn are still very much useful today. Gravity is a force that exists between objects that have mass. Every force that we encounter in the universe works on something. There's a certain property that is necessary for that force to have an action. And for gravity, that is mass. If you don't have mass, there's no gravity. Gravity doesn't affect you, and I guess you don't have to worry about learning this stuff if you don't have any mass. So gravity is the force that exists between objects that have mass. What Isaac Newton realized, or what he kind of worked out, was that the force of gravity, which we're going to call F with a little g beside it, force of gravity, is proportional to, which is a way of saying that it's somehow related to, the mass of one of the objects, I'll call it mass 1, multiplied by the mass of the other object. So even two pencils have gravity pulling them together. But because their masses are so small, as we'll see, we don't notice it. But the masses are still important. And then we have the distance between the objects squared. The further away you get, the less the force of gravity becomes. Okay? So as mass increases, force of gravity would increase. It's a direct variation. Whereas the force of gravity gets smaller if the distance gets bigger. See the difference? That's what we call indirect variation. So mass goes up, gravity force goes up. But distance goes up, gravity force goes down. So what Isaac Newton had to figure out was, what is this proportion? Is it 5 times this much, or 10 times this much, or 100 times this much? And what he discovered is that there is a number that makes this work. And he called that number a big capital G. And then the formula simplifies to this. Don't confuse the tiny subscript below the line and the exponents that are above the line. These ones on top are just telling us mass 1 and mass 2, but down below it's the distance squared. So let's just remind ourselves what all these things stand for. Obviously, Fg stands for the force of gravity. Now the big capital G is Isaac Newton's universal gravitational constant. Universal gravitational constant. What this means is that this number never changes. It's a property of our universe. It's universal. It's the same in every place on the universe. It's the same on Mars. It's the same on Earth. It's the same on the planet Zorbon in a galaxy far, far away. It doesn't matter where you go, this G number will never change. And we'll talk more about that in a second. Well, I can tell you the value of it. The number happens to be 6.67 times 10 to the negative 11. And it does have a crazy unit. We don't really care about its unit because the unit it has is just the unit required to make it fit into the formula to produce newtons as our force. But the unit, if I draw it here, let's see, it's meters cubed divided by second squared kilograms, whatever that is. That's the unit that we use for this concept. But nobody ever uses this unit. We just write the number. Because the unit, I'll show you what it's for. If you're going to get a force in newtons as a force of gravity, don't write this down, but just watch. Then a newton is the same as a kilogram meter per second squared, right? Mass times acceleration. We talked about that before. Well, if you look at our little formula, if you look at everything except the g, you have a mass times another mass, and you're dividing by a meter squared. That's the m1, m2, and the distance. Those would be the units of those things. So if you multiply that by this unit, when you put the g out front, you see what happens. The meters cubed are turned into meters. They kind of cancel with two of those. One of these kilograms cancels with that, and you're left with kilograms and meters per second squared, which is what the newton is. So the crazy unit isn't really a thing you necessarily have to worry too much about. Just know that it works and that it's there. It's the number that matters. And the number never changes no matter what. So that's the g. The other thing, of course, is if I move over here, we have m1, which is the mass of one object. And we have m2, which is the mass of the other object. Pretty straightforward. And we have this little r on the bottom, which stands for the distance between the two objects. Now let me show you why it's an r and not a d. Here's why it's an r and not a d. If I put an object here and another object, say right here, then the distance between them is this much. So the force of gravity then would depend on that distance. But what if I move the object over here, but it's the same distance away? Well, it wouldn't change the force of gravity at all. And you notice that this is like the radius. There's a circle all around this, and no matter where you go on the circle, you're the same distance away, right? So the force of gravity between these objects would be the same if this object was anywhere on the circle. In fact, you could even move the object out of the board by the same radius, and it would be like a spherical shell all around that's the same distance away. And so because it reminds us of the radius of the circle, we call the distance r instead of d. That also means we'll have to be careful about the direction of the force of gravity, but we'll talk about that a little bit later. Okay? So we don't need this. All right. Get rid of all this stuff here. Force of gravity between two objects. Let's actually calculate the force of gravity between two objects for fun. Okay? Let's say a 50 kilogram person is 2 meters away from a 30 kilogram person. Those are two objects. Let's find the force of gravity between these two people. How much force is actually pulling them together? Find the force of gravity between them. And this is pretty much plug and play, right? Fg, according to Newton, is equal to capital G, mass of one object, mass of the other object, divided by the square of the distance they are apart, distance between their centers, right? In fact, if I go back up here, I might want to change this, if you're writing the note, I might want to change this to read between the centers of the objects, to remind us of that. Because some objects are quite large. You have to, for gravity, you have to envision that all of the mass of an object is condensed into a tiny point at its center. in order for Newton's equations to actually make sense. Okay, so there's the equation. Let's plug in the numbers we have. We have a 50 kilogram person. Oh, sorry, we have G first. 6.67 times 10 to the negative 11. It's a very small number because the force of gravity is actually a very weak force. 50 kilograms and 30 kilograms. That part's simple. And then we said they were 2 meters away, so 2 squared on the bottom. And if you crunch this out in your calculator to see what number you would get, let's see, 6.67 times 10 to the negative 11 multiplied by 50 and then multiplied by 30 and then divided by what would become 4 gives us this number. The force of gravity between these two people is 2.5 times 10 to the negative 8 newtons, or 0.1, 2, 3, 4, 5, 6, 7, 8. That's how many newtons of force there is between two people standing 2 meters apart. It's insignificantly small. And this is why you don't smash into people you walk by in the hallway. Because the force of gravity between small objects, like these, is hardly worth noticing at all. But it could still be calculated for fun. And some of the questions on the worksheet I have for you will ask you to calculate, the force of gravity between two objects. I think there's one with 2 big ships. You'd think, well, ships are big. They should have gravity. Even if you made these numbers, 50,000 kilograms or 500,000 kilograms, those numbers would still be very small compared to this negative 11 exponent. And you'd still get only fractions of a newton. So even the largest objects we can think of don't have much gravity, except, of course, the Earth itself. And that's why we like to do a little shortcut. We like to consider the Earth sort of as its own separate thing. Since we feel Earth's gravity most, that's what we work with most, we want to make up a shortcut to deal specifically with the force of gravity between Earth and an object. So let's see what happens to his equation. If we change it to be the force of gravity not between two people or a bus and a lollipop or whatever, but the force of gravity between the Earth and the mass of, say, some object, which could be anything. Maybe it's a pencil, maybe it's a truck, maybe it's your dog, I don't know, aardvark, because they come first in the alphabet, in the dictionary. And then the distance between them squared. Now let's think about this for just a minute. To get our shortcut, we have to realize a couple of things. The G is a constant. It's a universal constant that never changes. So that number will never change. What about the mass of the Earth? Well, the mass of the Earth isn't going to change either. In every calculation you do, the mass of the Earth happens to be 5.98 times 10 to the 24 kilograms, but it doesn't change either. Right? The mass of the object that you were talking about, whatever is falling towards the Earth or feeling the pull of the Earth, that's variable. That could be anything. So that does change. Okay, we'll put a little box around that. That's the thing that could change if you were doing a question. Now let's talk about the distance between the object and the Earth, r. Let me draw a little picture. Here's the Earth. Here's the center of the Earth. So if you're standing here, then you would be 1 radius away from the center. 1 radius. And the radius of the Earth is 6.38 times 10 to the 6 meters. Or if I write that out, 1, 2, 3, 4, 5, 6. That's how many meters it is to the center of the Earth. Now let's see what happens if we take everyday objects. What if we were to stand up on top of a desk, say 1 meter higher? Well, if I jumped up 1 meter higher, so let's go on a desk, 1 meter high from the surface of the Earth. Well, that number would change to 6380001. Is that really going to make a difference? Probably not. In fact, if you look at the scientific notation, it wouldn't even show up there, would it? It wouldn't even show up in the number. So that's insignificant. It wouldn't change anything. Now let's go a little higher. Let's go to the top of, say, a high building. Let's go 350 meters up. Let's see if that would change. Well, 350 meters would make the number 6380350. Right, add it on. Well, look, it still would not show up in the scientific notation. When you round it off, it's the same bloody number, so it's not significant to be on the top of a building. Because you're still, like, watch, here you are on the surface, here you are on the top of the building, when you wouldn't even see it on the picture. What about if we go really high? Let's go up to where an airplane is. An airplane might fly, say, at 30,000 feet. 30,000 feet is about 10,000 meters. So let's put a 10,000 meters up here. And let's add that on. Now it would be 6.39000. Does that really even change the number? Not significantly. It still rounds off to 6.4 times 10 to the 6. So even as high as an airplane, if you were to draw an airplane on this picture, he'd be right there. It's not moving. So the point I'm trying to make is the region where humans live, in our little world, who goes lower than the surface? Not much. Who goes 10,000 meters below the surface? Nobody. The odd crazy miner, but nobody. And who goes higher than airplanes on a daily basis? Nobody. So for everyday things that we talk about, things that happen all around us, balls being dropped and dogs chasing cats and whatever happens, it all happens within this little red line here, which effectively is always this far away from the Earth's center. So if we stick on the surface of the Earth and we look at just that area, then this number r will always be 6.38 times 10 to the 6 meters, and it will never change either. The only way you could get a number bigger than this would be if you were to get in a rocket and take off high, high above the Earth. Then it might matter. But who does that on a daily basis? 99.9% of our lives are this far away from Earth, all the time, even if you're on a desk or in a building or on the ground. Even if you go undersea and dive down below the sea level, you're not going to dive down 3 kilometers. It doesn't matter. So there's a lot of these things that don't change if we consider the gravity between Earth and an object. So let's rewrite that, and let's just clean all this up so it makes some sense. So what we have is the force of gravity equals g, which doesn't change, the mass of Earth, which doesn't change. Then we'll put over here mass of the object, because that was the only thing that could change. And then we'll divide over here the r squared, which doesn't change. These three things do not change. So no matter where you are between the surface and airplanes, that's always going to be the same number. The only thing that seems to matter is the mass of the object. So let's crunch this out in the red circle and see what that comes out to. It turns out that this becomes, well, it would be 6.67 times 10 to the negative 11 multiplied by the mass of the Earth, 5.98 times 10 to the 24, divided by 6.38 times 10 to the 6 squared. Now, you can crunch that out on your calculator. And some of you are doing that, and you might suddenly realize that the answer you get is quite familiar to you. All of this gunk works out to 9.8. Which you're like, hey, isn't that the way gravity accelerates? Isn't that interesting how near the surface of the Earth, that's how much we measure the acceleration of gravity to be. And so if I look at what I've got here. I've got the force of gravity between the Earth and any object is equal to 9.8 multiplied by the mass of the object. And since we know this number is an acceleration, what we really have here is an m times an a. We have Newton's second law popping out just like that. So the force of gravity near the surface of the Earth, we know we're right about this because obviously there's the law. So what we can do is we can shortcut and we can say that the force of gravity between Earth and any object is equal to m. And guess what? What was the letter that we gave for this little number? We gave it a little name. Well, it's an A because it's acceleration, but we gave it a special letter. Because it was gravity, we gave it a little g, remember? So we call it little g. But little g is going to be 9.8 as long as you stay between, submarines and airplanes. As long as you're in that realm, it'll always be 9.8. It also has a fancy name. It's called the gravitational field value. Sometimes they call it the gravitational field constant, but it's not constant, it's only constant at the Earth's surface. So let's call it the gravitational field value at the Earth's surface. Unlike big capital G, which is the universal gravitational constant, which is never changing, little g does change if you go too high, the further you get away. Little g is only good from submarines to airplanes, as I showed you on the picture. Because if you go much further, here's our picture of the Earth again, where'd it go? Way up here. If I start to go further than airplanes, like the space shuttle, or even the moon, or something way out here, well now, I am a significant distance away from the center, and it'll start to change all the numbers. But as long as I stay on this little part here near the surface, from submarines to airplanes, then I can use this shortcut to figure out the force of gravity between the Earth and any object. And it's very easy. Fg equals mg. And I don't need to worry about all those exponents and scientific notation. I don't need all these other numbers because they're not going to change. So all I want to do now is just do a couple of quick examples to show you how they might work, and then we're good. So here's what I want you to do. I want you to find the force of gravity between Earth and the following objects. Okay, and I'll give you them. One will be a 5 kilogram box. 2 will be a 20 kilogram dog. And 3 will be a 250,000 kilogram truck. Giant transport. Okay, so go ahead. Using Fg equals mg, find the value of the force of gravity acting on those three guys, and we'll come back in a second and take them up. So what you should have done is you should have said the force of gravity equals mg. In this case it would be 5 times 9.8, which is 49 newtons. In this case it would be Fg equals mg, but that would equal in this case 20 times 9.8, which is 196 newtons, right? And then if you do it with the truck, it would be 250,000 times 9.8, which I think is 2,450,000 newtons. So that would be the force of gravity on these three objects. Now, I want to tell you something else. Another thing that's kind of important. The force of gravity, the force of gravity between Earth and an object is given a special name. It's an easy name. easier than writing the word object. Earth and an object, is called something we're very familiar with. It's called the object's weight. And weight is measured in newtons. Now you might say, wait a minute, that's not true. When somebody asks me how much I weigh, I tell them I weigh 40 kilograms. But 40 kilograms is not your weight. It is your mass. And although we use the terms interchangeably in everyday life, in physics, it's very important to keep them separate. Your mass may be 40 kilograms, but your weight is Fg, which would be 40 times 9.8 mg, right? So 4 8s are 32, 36, so you would weigh 392 newtons. That's your actual weight. But no one says that. People just say, well, I weigh 40 kilograms. That's because we can get away with it, because no matter what your mass is, you just multiply by 9.8. It's the same for everyone. So it's kind of like a shortcut to say 40 kilograms. But when you're dealing with physics, and if there's a question that asks you for the weight of an object, they don't mean its mass. They don't want kilograms. They want the newtons, and you must calculate the force of gravity for an object's weight. Or if you have a question that says an object weighs 400 newtons, that's not the mass. That is the force of gravity on the object. So the word weight is very important for gravity. Make sure you understand the difference between weight and mass. Okay? All right. And that is the end. We have a little worksheet to practice, and that's all for this video.